Now, ladies and gentlemen, when I started this video, I said I'm going to focus on the alcohols only, but now I'm thinking that let me just incorporate other homologous series so that everything will just make sense. Okay, just to quickly recap on what I've done so far, your alkanes, alkenes, and alkynes would have what we call the weak van der Waals forces. Now, your weak van der Waals forces can also be called your London forces or your dispersion forces. Please just take note of that. And then now, your haloalkanes would have what we call a dipole force. Now, why are we saying it's a dipole force? If you can remember, in grade 11, we used to identify a structure. Okay, now when you look at your alkanes are surrounded by hydrogens, which makes that particular structure to be nonpolar. Okay, but now the moment you add a halogen to the alkane, like I explained in the previous video, you would realize then the structure changes a bit. Why? Because your chlorine or your fluorine, whatever halogen that you're going to add, will come with its own electrons. Okay, now because this structure of an alkane together with your halogen will now have a side that is slightly positive and a side that is slightly negative, then it makes this entire structure to be what? To be a dipole, meaning it has two poles. One pole would be negative and the other pole would be positive. Now, this is with regards to your haloalkanes. Now, when you talk about your alcohols, you then realize that with alcohols, ladies and gentlemen, we have what we call your hydrogen bonds. Okay, the hydrogen bonds, if you can remember from grade 10, we had a situation where we were talking about water, right? And then we were saying that your water molecule is held together by what we call your hydrogen bonds. But obviously, when you further and further uncover this topic, you then realize that it's not only water, but it can also accommodate what we call your nitrogen and hydrogen, your hydrogen and fluorine. You can also have those types of compounds, and they are also having your hydrogen bonds. So your alcohols are again one homologous series that will have your hydrogen bonds. Right. Now, the next homologous series that we are going to focus on is your aldehyde and your ketones. Okay. Now, you would realize that these two families, they are very, very close together, but there is something that separates them. Now, if you look at your aldehydes, now your aldehydes would have a carbon with a double bond to oxygen, but now the rule is the carbon to the double bond to oxygen must be on carbon number 1 for this to qualify as an aldehyde. Now, for a ketone, guys, please let's not confuse the two. For a ketone, the double bond to oxygen, right, it's on carbon number 2 or carbon number 3 or carbon number 4, according to whatever number of carbons that you have for that particular structure. Now, the difference is aldehydes, your double bond to oxygen is on carbon number 1. Is that clear, guys? Now, for ketone, we have from carbon number 2, carbon number 3, carbon number 4, we have a double bond to oxygen. Guys, let's not confuse these two families. Though they have the same general formula and the same molecular formula, but the structure is different, which makes them, again, isomers. That's another topic, but for another day. But as long as we can be able to differentiate those two. Is that clear, ladies and gentlemen? Now, your aldehydes, they have the suffix al, and then your ketones, they have the suffix on. Say, for instance, I want to name an aldehyde. Number 1, I know that the double bond to oxygen is on carbon number 1. Okay? Say my longest chain is 3. So if my longest chain is 3, when I name this particular organic compound, I'm going to say propanal. Is that clear? Now, for this particular compound to qualify as a ketone, that means I need to shift the double bond to oxygen. I need to shift it to carbon number 2. So as soon as I shift it to carbon number 2, still on the same chain that has the longest chain of 3, then it becomes propan 2 on. Why? Because the double bond has shifted from carbon number 1 to carbon number 2. Is that clear, guys? Carbon, if it's on carbon number 1, it's an aldehyde. If it's on carbon number 2, then it becomes what? It becomes a ketone. And then one thing that we take note of is that the type of intermolecular force that we get here is what we call the dipole force. Why? Because of the oxygen. Because of that double bond to oxygen. Your oxygen, remember, comes with its own electrons, so it makes the entire structure positive and negative. In other words, I will have one side that is positive and I will have one side that is negative. Please, let's just take note of that. So your aldehydes and your ketones would have what we call a dipole force, which is also a strong van der Waals force. Right, now the two last homologous series that we have, it's your carboxylic acid, and then we also have your esters. Now you would realize that again with these two homologous series, the general formula is the same, the molecular formula is the same, but the structure, it's not the same, which makes them what? Which makes them isomers. Now let's look at the carboxylic acid alone. Now your carboxylic acid would end with the suffix oic acid. So when you name them, you need to mention the word oic acid. Okay, please let's just take note of that. And then now when I name this particular homologous series, okay, I need to realize that now I must have a double bond to oxygen as well as a single bond to what? To the OH. I'm going to repeat that again. I'm supposed to have a double bond to oxygen as well as a single bond to OH. Please let's take note. This is on the same carbon. In other words, one carbon, double bond to oxygen, single bond to OH. Guys, let's not separate those two. You cannot have a situation where your double bond is on carbon number 2 and your single bond to OH is on carbon number 1. That is not how the carboxylic acids are supposed to look. We have on one carbon a double bond to oxygen and a single bond to OH. So that's how we identify this type of what? This type of homologous series. And now the name of the functional group for this particular homologous series is called the carboxylic, or the carboxyl, if you may like. It's called the carboxylic or the carboxyl. That would be the name of the functional group of this particular organic structure. Now for your esters, ladies and gentlemen, your esters are a combination of two homologous series, which is your alcohol and your carboxylic acid. When you take these two families and you remove water and then you join the two structures, then we form an ester. Okay, so originally we would have an alcohol and then we would have a carboxylic acid. You join the two structures, but first we remove what? We remove water. But we don't just remove water. There must be something present, because unfortunately this type of a reaction between the two families, it's not spontaneous. So it requires a catalyst. Catalyst by the name of what? By the name of sulfuric acid or phosphoric acid. As soon as you add this catalyst to the two structures, then the catalyst becomes a dehydrating agent. So in other words, it removes water for us to form what? To form an ester. Okay. Now, the type of intermolecular force that would be found then in these two structures would be your the hydrogen bonds as well as the dipole. Now, which makes them the strongest, okay? But take note, for your ester, I have a dipole force. Is that clear? Now, but for a carboxylic acid, guys, I have a dipole and a hydrogen bond. So between these two structures, your ester, in terms of the intermolecular force strength, it will be less than your carboxylic acid. Your carboxylic would be the strongest. Why? Because it has the presence of your dipole together with your hydrogen bond. I hope we can find the difference between these two families. Now, when we name your carboxylic acid, say for instance I have 2 carbons in my chain. Okay, remember, in that particular structure, I'm expecting one of these carbons to have a double bond to oxygen and a single bond to the OH. Okay, so I'm going to name this to be what? To be ethanoic acid. And another name again for ethanoic acid is acetic acid, and another name is what we commonly know as your vinegar. Okay, so your vinegar is your ethanoic acid, and it's also called the acetic acid. Obviously, the difference will be the percentage. Okay, now when you get to the esters, your esters, as I mentioned, they are formed by two structures, which is your alcohol as well as your carboxylic acid, and then we've joined these two structures and then we removed water. Now your alcohol becomes the branch, your carboxylic acid is the one that becomes an ester. Say for instance I want to name this particular ester. Say my alcohol had one carbon and then my carboxylic acid had two carbons. Okay, now when I name this, because my alcohol becomes a branch, I am going to say then methyl. And remember, branch with the "ile", okay? And then for the carboxylic acid, remember, with the carboxylic acid, what did I do? I removed a hydrogen there, okay? So that I can open space for what? For the branch that's going to join the ester. So in this case, because my carboxylic acid would have two carbons, then it means it's going to be ethanoate. So that means my suffix for the ester would be oate. Okay, so when I name the entire structure, I am going to say methyl ethanoate. Okay, that brings us to the end of the lesson. I hope that you enjoyed, ladies and gentlemen.